Okay. Okay, so this is a collaborative work with several colleagues from Lawrence Berkeley Lab and colleagues from Livermore, Paniaut, Vasilevsky, and Andrew Barker, and also Delian from University of Colorado. So we developed, recently developed a new multi-grid solver and also the coarse-grid solver to help this multi-level algorithm. So I'm mainly focusing on the majority of the talk is about a coarse-grid solver. But I'll give you a high-level overview of this element-based multi-grid solver. Okay, so the outline is the spectral element AMG. And there are two big components that are time-consuming. One is setup hierarchy. That's not something you see from geometric multigrid or even from a hyper kind of AMG. And then the coarse-grid solver is critical. And I'll spend quite a bit of time talking about the performance characterization of this type of solver and what we have been doing with the new machine, the multi-core optimization. Especially, we spent quite some time to understand the performance limit of the solver on the Intel mic, for example. So the high-level bullets, the highlights of this multi-grid solver is pretty much can be summarized here. It's a smooth aggregation spectral element AMG. You can consider this as a combination of geometric multigrid. Yeah. Oh, there. Thank you. It takes, let's say, take 30 seconds.
30 seconds?
Yeah. Hello? Is my call? Oh, yeah. No, it's better.
A little bit higher.
So that's better. I don't need to shout. Still shout. So it's a combination of geometric algebraic. The geometric part is coming from the upfront driver is finite element discretization. And then after that, everything else is algebraic. Coarse-grid solver is also algebraic. And the nice thing about this is the coarse space. There's a theoretical foundation that Paniaut, his co-authors, they have developed is coarse space has a very nice approximation property. So it's operator dependent. You can, for different PDEs, you actually take advantage of the operator property. And then for elliptic PDE problems, you can solve the eigenvalue problems locally, independently, embarrassingly parallel to build this hierarchy. And this code, as AMGe is already released, you can download from the Livermore website. For more general problems, saddle point problem, indefinite problem, the local problem, the hierarchy is built by SVD, solving the SVD problems. Currently, this code, par-elag, is still a prototype code. It's not quite released yet, but in the summertime should be ready. And as I mentioned, the novelty of this AMG is the hierarchy, the way they built the hierarchy. This can be reused, can be employed for nonlinear PDEs, parametric PDEs, and also the Markov chain Monte Carlo simulation. So to start with, you have finite element discretization, and you partition the finite element mesh into the different regions. Each of these blocks is called agglomeration. And then between the two regions, there are vertices shared between the two agglomeration. So you use some scheme to divide, to put the vertices, assign them to one of the two regions. So then you get the vertex partition. So that becomes aggregates. So when you say the vertex partition like this is the aggregates. So you have a lot of the little, small subdomain like that. For this AMG method, you can use high-order elements to discretize PDE. So that's one advantage. And the AMG solver is pretty standard. So you have fine grid to do the pre-smoothing. You can use some polynomial smoother here, or a simple one, stationary iteration, cheap. And then the critical part is a coarse-grid solver correction. So you use your interpolation matrix P to restrict the residual to the coarse space, and then solve the coarse space problem, interpolate back this into the fine grid. At the fine grid, you do the post-smoothing. So that's the two-level algorithm. The way to get a multi-level algorithm is to solve this coarse-grid problem recursively using the same algorithm. Then that's the multi-level, multi-grid idea. But another thing is for coarse-grid solver, you have a lot of options. The simple one is PCG, and you can even use a hyper kind of AMG to solve this coarse-grid. And now we're using the new factorization, approximate factorization HSS solver to solve this. So for the hierarchy, as I mentioned, the hierarchy is fairly involved, expensive in this multi-grid solver. So what do you need to do is to find this P matrix, interpolation matrix, that your coarse-grid matrix is P transpose AP, is a smaller dimension. And in this particular spectral element method, P is computed from the lowest eigenvectors of each of the aggregate local element matrices. So each of these PI are small eigenvalue problems. They are independent, entirely parallel. And after the first, you find the eigenvalue, solve the eigenvalue problems, you use some polynomial smoother, a polynomial smoother to multiply this for a few times and to get a better approximate coarse space. Computationally, you see that there is this S times P is a sparse matrix, sparse polynomial of matrix A, multiply this. So it's a sparse matrix multiplication. And then to get a coarse-grid AC is sparse matrix, sparse matrix, sparse matrix. So it's a triple sparse matrix product. So that's the computational kernel and then the eigenvalue problem for building the hierarchy. And two improvements that we have made is one is to replace the direct eigensolver in LAPAC by sparse ARPAC plus SuperLU in the shifting invert mode. So this is a projection method. This will reduce the problem to smaller ones. Another thing is we have developed an earlier termination criteria for ARPAC so that we can monitor the accuracy of already computed eigenpairs, and then we can stop earlier. That actually helps a lot. So with these two improvements, we get 2 times faster for the overall total solution time. And this was, the detail was given yesterday by Osni in his talk yesterday. And also recently, our paper for ICCS this June conference is accepted, which has, you can download the paper to get all the details. So the other component is the coarse-grid solver. And what we are doing right now is to use a more sophisticated approximate factorization algorithm to replace the simple PCG. So this algorithm is low-rank hierarchical semi-separable sparse matrix factorization. The goal here for this low-rank factorization is to lower the arithmetic complexity. Traditional LU factorization, like SuperLU, for many PDE problem is order of n squared. Now we can cut it down to order of n or order of n polylog n. So that's an improvement for arithmetic. And the approach is hierarchical matrix algebra, like H matrix, H square matrix, etc. So the foundation of this is actually, the mathematical foundation is very much the same as the fast multipole. So in the fast multipole, you have the term concept of far field, near field. And if you put into the matrix context, far field is just the off-diagonal block. Near field is the diagonal block. So what in matrix term you can do is for far field off-diagonal block, you use the compression, like SVD compression. Remove all the singular vectors corresponding to the smallest singular values. So that's the idea. And if you do this only for one level, you won't get asymptotically faster algorithm. So you have to do this in a multi-level hierarchical way. That's what this picture is about. All your orthogonal vectors, they use nested property, so that you get the representation is much smaller. That's how you get almost a linear time, both in time and in memory. So this code, StrongPack, is released almost, let's say, less than a year ago, but we already got about 200 downloads. People use it in various applications. So for example, for BEM matrices, we have observed over 5 times faster than the traditional LU. And for traditional, for the sparse problems, those are relatively difficult problems from SciDAC applications. So like the nonlinear MHD equations and accelerator Maxwell equations, we have seen like over 7 times faster than traditional sparse LU, and a significant reduction in memory. So this was discussed in detail in yesterday Peter's talk. And also we have a number of papers which you can download to see the details. Okay, so let's take a look at the performance of this algebraic solver. How much time I have? 10 minutes? 10, yeah. Okay. So a good benchmark is a relatively harder problem is this oil reservoir simulation. And the problem is difficult. It's because of the PDE has jump coefficients. So the PDE we're solving here is Darcy equation. This is the PDE problem. And K is the permeability of the medium in the region. And the problem here, the difficulty is because K is changing in very big, jump, the magnitude is very big. So that's the picture of the plot of this K of X in this region. So you can see that there are 2 layers. Roughly, you can see the 2 layers of the soil. They're a mixture of rocks, sandstones, etc. And then if you plot this K permeability, the difference, the magnitude difference is more than 10 times. So it's 1 order of magnitude different. That could cause a problem for many standard algorithms. And then one thing we like to bring out is compared to geometric multigrid, the coarse-grid matrix here, the sparsity pattern is very different. So this is the, after discretization, finite element discretization, you got a fine grid matrix has very nice pattern. If you do geometric multigrid, the coarse-grid is essentially the same pattern. But for this, we're doing this, using this P is computed from the eigenvectors, dense eigenvectors. After you multiply S times P, then that's your coarse-grid matrix. So the first thing is dimension is reduced by a lot. So it's more than 100, it's, 50 times, I don't know how many times reduction in the dimension. So that's very different from geometric. Geometric for 3D problem, usually you get an 8-factor reduction. Another difference is the coarse-grid is much denser. This is the number of non-zeros per row. It's 180, but here it's only 26, the finite element, okay? So that's the problem we need to solve at coarse-grid. Okay, so let's take a look at what kind of optimization we can do on this newer multi-core machine. And this is the nice corner. The next generation will be nice landing. It will be even more complicated. So this card, each card has 60 cores. They are arranged, connected by this bidirectional ring. And each core has a L2 cache, okay? The trouble here is the L2 cache is private physically, but they are maintained coherent using this bidirectional ring, okay? And another difficulty with this machine is the SIMD vector is very wide. So they have SIMD register of 8 double precision flops per cycle. You need to vectorize your code. That's something we have forgotten for many years. So let's take a look at the coarse-grid matrix. Suppose this coarse-grid matrix is the iterative solver, PCG. Then your vectors, you partition among those 60 cores by block row. Then your vectors will have a large amount of components that are shared among different different cores. So in particular, this matrix has a very wide bandwidth. So you could imagine that 30 of the cores, they will have some component they share. So when you update, and once they share this component, they need to load into private cache. But once you update one of the components, the update incurs in cache invalidation and make sure it's coherent. So you are going to go around this ring, I don't know how many, on average 30 hops. So 30 of those processors, they need to incur 30 updates, each 30 hops. So that's expensive. So that's one of the things that need to be aware of this kind of architecture. So the time breakdown of this AMG cycle, it's smoothing takes a lot of time at the fine grade, the two smoothers. And then if you use the PCG, it scales very well, but the problem is this region. So that's the area we are attacking, trying to see whether we can get it to scale better on 32, 60, 128 threads. For multi-core, you usually just use OpenMP, right? And our first algorithm is simple. For each of these operation, the CG operation, sparse SPMV, you do a parallel 4, and dot product parallel 4, and so on. So altogether, you have 7 of these parallel 4. Each of these parallel 4 is a fork join. Okay, so fork, you need to pay the cost. Join is a synchronization, some cost. You have 7 of these lining up. That's not very good. So one improvement we have been doing is we say we'll do one fork, one big single parallel region. And we let the threads alive here do a lot of work. And here it's the same code, right? We just reorganize so that for some of the operation like this, we'll do single thread. It's a scalar update, a single thread. We don't need a parallel, so it's a single thread doing this. The other thread could move ahead. But this single requires synchronization, so that's a synchronization point. And similarly, SPMV here is OpenMP4. You do parallel, but no wait, so you can move ahead, okay? So then with this optimization, you got one fork join region, but you have 3 synchronization points. So the next question is whether we can reduce the synchronization. And the last algorithm I'll show is this one. We still have one fork join region, and we do only SPMV parallel. But the rest, these operations, they are relatively small. We just let one thread to do it, so it's OMP single. So the interesting thing is we have discovered that for this operation, if you use all threads to do parallel compared to one thread to do, actually this version is slightly better. 2 minutes? Okay. Wow. Okay.
Parallel is the matrix vector multiply.
SPMV is parallel, it's multi-threaded. Okay. So that now you see the good news with the algorithm 3, we got a scalability. Okay. So that's this. And then I want to show the 2 minutes, right? 1 minute. Okay. So Roofline model is actually very interesting. This. So for the algorithm, the Roofline model, intuitively, it's very simple. It's just the runtime is the maximum of memory access time and the flops time. Assuming memory access flops, they overlap entirely. So you just take the max of this. That's your runtime. And for the simple algorithm, like a coarse-grid PCG, then you can count everything, the bytes, how much memory you need to stream all this data from DRAM to the processor, and the flop count. And you use the amount of bytes divided by the DRAM bandwidth. That's your memory access time. At least you need that much time. And the flop rate of the machine divided by the flop count divided by flop rate, that's the time you need, the minimum you need. So with this characteristic, then we just look at this machine. It's an Intel Ivy Bridge machine. So the memory bound is given by this with a number of cores. This is a 1 socket, 12 cores. And the flops bound is given by this. So in the beginning, the algorithm is memory bound. It's a flop bound. In later, it's memory bound. And our after optimization of actual one is not so far away from the gap. So you can see that for the coarse-grid PCG, we got 23% close to the bound. And for the HSS, it's much harder, complicated algorithm. The bound is looser. So then one thing I want to bring out is this kind of algorithm has a lot of parameters. So for example, you can say choose the coarse-grid solver, how many elements per agglomerate, then the polynomial degree when you do the smoother, and the spectral tolerance, how many eigenvectors you want to retain to build a hierarchy. So after you multiply all these together, there are 16 configurations. Then you run the code. For example, this Babbage is the night corner, the 60 cores multi-core. You can see that with HSS, it's improved. And PCG, it's slightly slower. This is runtime. But then between the worst percentile, this is the percentile of the fastest versus the worst. The magnitude, the runtime magnitude can be 1 order of difference, 10 times difference, if you are not, you're unlucky choosing a bad parameter. And then our multi-level code is relatively new, so we have some result, but it's not very conclusive yet. But the good news is the HSS coarse solver has improved over PCG if you use this factorization. So that's our software component. All these, the finite element, you can use the Livermore MFAM, and the SAAMGE for symmetric positive definite, par-elec for indefinite, this from Livermore, and then StrongPack is from Berkeley. Okay, so we're still fixing some scalability issue for the multi-level MPI code. So then the parameters, as I mentioned, greatly influence performance. So we are developing the auto-tuning framework to help user to select parameters. And then the performance model is actually, this helps us a lot when to stop optimization, because based on this limit, then we don't need to do further optimization. So this needs to be extended to multi-level code and also the multiple nodes with big MPI communication stuff. Yeah, so let me stop here. Thank you.